Ah, for the good old days. Wasn't that a beautiful Model T? And then again, wasn't that a beautiful BMW? It all depends on your point of view. But one thing is for certain. The old cars were easy to repair. Well, things have changed. Added conveniences and government regulations, anti-skid and airbags, four-wheel drive and four-wheel steering, even environmental temperature control. The method? Electronics, computers, the little black box.
The Corporate Training Department of Standard Motor Products presents this video training program as part of our continuing effort to keep you up to date on how to repair today's cars and remain profitable. This high-grade fuel systems training module covers the Nissan Electronic Fuel Injection systems. In order to confidently and profitably repair these systems, the mechanic must have certain hand tools and test equipment. Also, he should have a working knowledge of the basics of fuel injection and have an understanding of engine computer control systems. He should also be familiar with the concept of open loop and closed loop. And most importantly, he should be familiar with electrical and electronics diagnostic procedures.
By now, I'm sure you're wondering, where is this program going? What will I learn? I don't work on import cars. Well, you're not alone. But what is a Ford Probe? Who makes the Chevy Nova? It's probably safe to say that aside from factory dealers or import specialists, the average mechanic is not comfortable with what he knows about import cars. So as you follow along with this video program, we will supply all the information needed to profitably repair Nissan fuel injection and computer control systems. Ready?
This Nissan, you will see, can be easier to repair than the average Ford or Chevrolet. Late model Nissans are equipped with a sophisticated onboard diagnostic system. Let's briefly review some general information about Nissan's fuel injection systems. There are two systems. One uses a vane meter input to the computer. This early system used on the Stanza, Maxima, and Z car is called EFI. Another is called ECCS, Electronic Concentrated Control System. This style uses a hot wire mass airflow meter on most applications, but some use the vane meter. Before we actually begin working on this system, what is it trying to accomplish? What does each component do? And how do they interact with each other to affect the operation of the vehicle? Well, the main objective of the entire system is to allow the vehicle to give good fuel mileage and clean emissions, but not at the expense of good acceleration and smooth operation. All fuel injection systems can be split into three basic subsystems. 1. The air management system. 2. The fuel control system. And 3. The influence of the engine computer on fuel and air delivery. As you can see from this Maxima, the components in the air management system consist of the air filter and ductwork, the airflow sensor, a throttle plate and butterfly, an air plenum, and also a throttle valve switch. The fuel system consists of an electric fuel pump mounted inside the fuel tank. Its output goes through a filter mounted on the firewall. The fuel is then supplied to the fuel rail and to each of the injectors. Pressure is maintained at 20 to 37 pounds per square inch, or 179 to 255 kilopascals, by the pressure regulator mounted on the end of the fuel rail. Excess fuel not used by the fuel injectors then flows back to the tank. As you can see, the regulator receives a vacuum control signal from a control solenoid. Note the fuel temperature sensor. On this Nissan Stanza, the air enters through the air filter and travels through a vane airflow meter. This system uses an intake air temperature sensor. The air flows through the ductwork to a throttle plate. Notice it has two butterflies. The fuel system is similar to the Maxima. The details of the EFI control system show the engine control computer receives sensor input readings from the distributor or IC unit, sending an engine speed signal. The vane airflow meter, which measures the amount of intake air and air temperature, A water temperature sensor signals engine temperature. A throttle valve switch. The exhaust gas oxygen sensor, part of the feedback system, gives a reading on the amount of oxygen in the engine's exhaust. An ignition switch signals the computer that the vehicle has started. A transmission switch tells the computer which gear the vehicle is in, and of course, a battery supplies power. The engine computer calculates the primary fuel injection pulse width based on signals supplied by the engine distributor and vane airflow meter. In addition, the onboard computer memory can supply various amounts of fuel enrichment or fine adjustment to the base control mode to meet special situations. The other control sensors trigger the pre-programmed enrichment modes. To assist in fuel enrichment for startup in early EFI systems, a cold startup injector and thermo time switch were used. Now let's take a closer look at some of the components in the ECCS system. The engine's control computer receives sensor inputs from a crank angle sensor, which supplies engine speed and piston position. Unlike the EFI and domestic systems with the Hall effect or magnetic pickup arrangements, this system uses a photo-optical distributor. A what? It's simple. As you can see, the distributor has a wheel with 360 outer slits cut into it. Inside are 6 larger slits. This system functions by using an LED or light-emitting diode to transmit light onto the wheel. A light-sensitive receiver or photodiode senses the light that shines through the slits and triggers the computer control circuit. That is, each time the light shines and is cut off, the computer receives a signal. The 360 slits signal engine speed. The 6 slits relate to each cylinder's position or crank angle. Next, an input from the mass airflow sensor, or a vane meter, which measure the amount of intake air. A cylinder head temperature sensor. An exhaust gas oxygen sensor. A throttle valve switch to measure throttle position. A transmission switch, a vehicle speed sensor, an ignition switch for a start signal, and a fuel temperature sensor. In this system, the engine computer calculates a basic fuel injection pulse width by receiving signals from the crank angle sensor and the airflow meter. The ECCS computer then takes other sensor readings and makes fine calculations to adjust pulse width for each particular enrichment program. This system operates in 2 primary fuel control situations. 1, mixture ratio feedback, and 2, fuel enrichment or a computer program control. Fuel enrichment will occur during startup, warm-up, during prolonged idle, under heavy engine load, when the cylinder head temperature is extremely high, or during acceleration. Remember, 2 types of intake air measurement devices are used. 1, this mass airflow sensor, a hot wire style. It has a burn-off mode or self-cleaning mode capability. This hot wire measures the mass of the incoming air, not just the volume. The air coming in through the intake system passes over this heated wire. The wire is cooled, and more electrical current must be passed through it to maintain its temperature. The measurement of this electrical current flow through the wire is calculated by the computer. The other style is this vane airflow meter. It does a similar job of measuring the mass of the incoming air. In this system, the air temperature is measured by this temperature probe. As the air passes through the system, it moves this door. The door is connected to a potentiometer or variable resistor. The computer takes a calculation of the door position and therefore the amount of air entering the engine. The temperature and door position together supply the computer with a reference signal of the mass of the incoming air. The position of the throttle valve is critical to the operation of the vehicle. The throttle valve switch is attached to the throttle chamber or throttle body, and it moves in response to accelerator pedal movement. The switch has 2 contacts. One set supplies the computer a voltage signal for idle position. Another set supplies a voltage signal if at full throttle. Note this is not a potentiometer. Only 3 possibilities here: idle, run, or full throttle. The next components control the engine idle speed. In the EFI system, the engine utilizes an idle speed control valve. In this case, the engine control computer, using an engine speed signal, adjusts the engine idle speed to compensate for load from the accessories. The computer responds with on-off voltage pulse to energize an idle solenoid valve. The idle-up solenoid valve is nothing more than an air bleed or an air bypass of the closed throttle plate. The fuel temperature sensor is not used on the EFI system, only on the 3-liter V6 ECCS system. The fuel temperature sensor must be replaced as a complete assembly with the pressure regulator if either malfunction. It aids the engine in starting under hot operating conditions by cutting off the intake manifold vacuum signal to the fuel pressure regulator. If the engine fuel temperature is above 40 degrees centigrade or 104 degrees Fahrenheit, the computer reacts, controlling vacuum for about 30 seconds. If the fuel temperature exceeds 70 degrees centigrade or 172 degrees Fahrenheit, it cuts off the vacuum signal to the fuel pressure regulator for about 3 minutes. Let's take a look at the fuel pump control system. The computer uses an engine temperature reading and a throttle valve reading and allows the fuel pump to operate. With the ignition switch on, the fuel pump relay is energized for starting and running of the engine. If the engine cranks but does not start, the fuel pump will cease operation after 5 seconds. The engine switch must be cycled off and then back on again to allow the fuel pump to run. If the engine were to stall, the fuel pump stops as a safety measure after 1.5 seconds, preventing the fuel pump from supplying fuel in case of an accident. In both the EFI and ECCS systems, the engine control computer has built-in diagnostics. The EFI system is not as sophisticated as the ECCS system, but will still supply trouble codes with a series of blinking red and green LEDs in all years except certain 1984 models. The trouble codes will be retained in memory. In either system, the trouble codes will be displayed only when self-diagnostics mode is called for. But the computer is constantly checking the system for a malfunction and will retain codes for 50 cycles of the starter system. The ECCS system also is equipped with 3 fail-safe or limp modes. If the airflow meter output reading is extremely low, or if the computer judges that the flow meter has malfunctioned, the engine will still be allowed to run as long as the speed is kept below 2,000 RPM. A second fail-safe mode triggers if the cylinder head temperature sensor circuit opens. The ECCS computer will allow the engine to operate in warm-up enrichment mode only. The third mode controls the engine if there is a malfunction in the fuel pump circuit. The fuel pump will receive power through an alternate circuit until the next time the engine is stopped. At this point, the fuel pump will no longer be allowed to pump fuel. To enter the self-diagnostics mode, a small screw on the side of the computer must be turned. It should be noted that the computer cover has been removed for illustration purposes only. It is not recommended as normal practice. In this Maximo with ECCS, you can see that the computer is located under a front seat. The ECCS system contains 5 separate diagnostic modes. Mode 1 is called Mixture Ratio Feedback Control Monitor A. Mode 2 is called Mixture Ratio Feedback Control Monitor B. Mode 3 is the Self-Diagnostics Display mode. Mode 4 is a diagnostic test for switches on and off, not unlike a Ford wiggle test or key on, engine off test. Mode 5 is a real-time diagnostics mode. In this mode, the vehicle can be driven on the road and it will detect instantaneously any malfunction in the fuel computer, ignition, or emission operating systems that display trouble codes. The early EFI system has only an on-off switch on the computer. In the off position, the fuel mixture ratio can be checked. To display encoded trouble codes, the switch must be turned to the on position.
That's it. We have covered the basic components and functions of the Nissan EFI and ECCS engine control systems. Now, to repair some common problems. Hands-on experience may be the best teacher, but through the use of video, we can simulate everything except your hands actually touching the components. Ready to repair some common problems?
The customer is complaining that the vehicle is getting extremely poor fuel mileage. It stumbles or misses and runs very badly when it is cold, and it just doesn't run the way it used to. Ask the customer the questions necessary to determine exactly what his complaints are. Remember, you can't diagnose a problem that doesn't exist. Keep in mind that self-diagnostic systems cannot troubleshoot everything. There are certain things that should be checked visually or with some simple test equipment before beginning to work on the fuel system or the engine control computer. Observe that working on this vehicle requires no special test equipment or tools. The first step in diagnosing this vehicle after the visual inspection is to remove the engine control computer from underneath the passenger seat. Do not disconnect the wiring. Position the computer so that the LEDs are clearly visible. Proper procedure calls for checking the idle speed. It should be approximately 650 to 700 RPM, depending on altitude. Next, check the ignition timing. It should be at 20 degrees before top dead center. And lastly, we should verify the CO reading. It should be 0.2% to 4% at the tailpipe. If you do not have a separate CO meter, you may utilize Mode 2 in the self-diagnostic system. Let's check the vehicle using the onboard computer. First, enter Mode 2, the compensating mixture ratio test. Turn the ignition key on. Turn the computer screw fully clockwise. The computer lamps will flash the test mode. 1 flash, 2 flashes. After the 2 flashes, quickly turn the screw fully counterclockwise to lock in Mode 2. Now, start the engine. Watch the green and red LEDs. They should alternately flash on and off at approximately the same ratio. On, off, on, off. If the green light is off more than it is on, it indicates a rich condition. If it is on more than it is off, it indicates a lean condition. Remember, this function only performs in closed-loop operation. If the vehicle is in open loop, the red inspection lamp will remain off. At idle, the lamps seem to be fairly even. Let's accelerate the vehicle to approximate a cruise condition. Notice as we accelerate the vehicle, the green lamp remains off more than it is on, indicating a rich tendency. Hold the engine at about 2500 RPM. As you can see, it is still remaining off a greater percentage of the time than it is on, still indicating a rich situation. What would cause a rich mixture? With the engine turned off and the key on, enter Self-Diagnostics mode number 3. Turn the diagnostic selector screw fully clockwise. When the lamps flash 3 pulses, immediately turn the screw counterclockwise. With the system in mode 3, let's watch for trouble codes. 4 flashes of the red, 2 flashes of the green. 4 flashes of the red, 2 flashes of the green. Code 42, indicating that the fuel temperature sensor or the sensor circuit is out of specification. Can this create an abnormally rich fuel mixture? No. The symptoms of a malfunctioning fuel temperature sensor are difficulty in starting a hot engine. Other than that, it should not affect the operation of the vehicle. Since no other codes are present, whatever was causing the difficulty in starting and generally poor running has either not set a trouble code or the computer is not designed to monitor the component's function. But before we begin individual component testing, do a real-time diagnostics test. That is, lock the computer in mode 5 and do a road test. The computer can instantly pick up any component malfunctions, even intermittent problems, if the malfunction takes place while we are road testing the vehicle. Let's begin the road test. Remember, we must operate the vehicle to simulate the customer's problems. There it is, the signal for a malfunctioning airflow meter, a code 12. One flash of the red LED followed immediately by 2 flashes of the green LED, repeated by 1 flash of the red and 2 flashes of the green. A code 12. Let's continue and see if any other codes are picked up. A 42. A fuel temperature sensor problem. With the car returned to the shop, let's inspect the airflow meter. First, check the harness and the connecting points to make sure that there is no problem with the plug, loose connector, or corrosion. Utilizing a high impedance digital volt ohm meter, we will do a power source inspection. With the ignition switch on, check the voltage between terminal E and ground. It should be receiving battery voltage. If there is a problem, check the harness continuity between the airflow meter and the battery, referring to the appropriate circuit schematics. Next, inspect the ground circuit. With the ignition key off and the airflow meter harness disconnected, check the resistance between terminal C, D, and ground. It should be approximately 0 ohms. If there is a problem, recheck engine ground and harness for continuity. We need to check the engine computer input signal to the airflow meter. With the meter reconnected, start the engine. Make sure the voltage between the engine control computer, terminal 31, and ground changes as the engine RPM is increased by the accelerator pedal. And output voltage should change from 2 to 4 volts. If it does not, replace the airflow meter. With the airflow meter replaced, check the fuel injection temperature sensor circuit. The resistance should vary with temperature. Utilizing a digital volt ohm meter, check the resistance from the fuel temperature sensor to ground. As you can see, no continuity exists in this fuel temperature sensor. If this is the case, the sensor is defective. Remember, the fuel temperature sensor must be replaced with the fuel pressure regulator as a complete assembly. It is a simple matter to replace the fuel regulator. First, remove the fuel pump fuse. Run the engine out of fuel. Now replace the regulator. Exercise caution while installing the new regulator to assure that the fuel connections are tight and leak-proof. Before restarting the vehicle, reinstall the fuel pump fuse and erase code 22, indicating a fuel pump circuit malfunction. To erase trouble codes, turn the ignition key on. Turn the diagnostic screw fully clockwise. Leave for 3+ seconds. Then turn the screw fully counterclockwise for 3+ seconds. Turn the key off. We have repaired the fuel temperature sensor and regulator. Replace the airflow meter. Next step would be to either rerun mode 3 or do a road test with mode 5. No codes present, but you feel that the car is still not exactly the way it should be. If it is run very long in a rich condition, it is possible to have contaminated the O2 sensor. We can verify the feedback loop at this time by rerunning a mode 2 test and watching the red and green LED. They are still indicating a rich running condition, though not as bad as before. The best way to diagnose this problem is to install a fuel pressure gauge and do a pressure test. Check the vacuum control system and do a balance test. With the gauge properly installed between the fuel filter and the fuel rail, restart the engine. Check for fuel leaks and allow the engine to run. Read the fuel pressure on the gauge. At an idle, it should be about 30 pounds per square inch, or 236 kilopascals. Momentarily accelerate the engine. The pressure should increase to 37 pounds per square inch, or 255 kilopascals. Stop the engine and remove the fuel pressure vacuum control line. Plug the hose leading to the engine and connect the hand vacuum pump to the fuel pressure regulator. Restart the engine. At 0 inches of vacuum, the pressure should be 36 to 37 pounds per square inch. Now, increase the vacuum in steps and monitor the fuel pressure. Remember, fuel pressure should decrease as vacuum increases. Stop the engine. Reconnect the engine's vacuum source. We have verified that the vacuum control system and fuel pressure regulator are operating properly. Next, we can do a fuel pressure balance test. On certain engine applications, this may be very difficult to perform. A balance test fires each individual injector. For a set period of time, while the injector is being fired, you will monitor the pressure drop. Turn on the key and charge the fuel rail. Turn off the key. Fire the injector. Note the pressure drop. Charge the rail. Connect the tester to the next injector and note the pressure drop. Follow this sequence through all 6 injectors. You are looking for 1 or 2 fuel injectors that do not fit into a pattern. That is, they may have a very large pressure drop. Also, with the rail charged, the fuel pressure should maintain. It should not be dropping off. If there is a pressure, it would indicate a leaking injector, and consequently, a richer fuel mixture. For illustration purposes, we will quickly review injector replacement on this vehicle in the event that the injectors would have to be replaced. First, with the fuel pump fuse removed from the fuse panel, run the engine until it is out of fuel. Then turn the key off and reinstall the fuse. Remember to clear code 22. Carefully disconnect the fuel pressure line and the fuel return line. Then disconnect the air duct, the accelerator cable, and the cruise control cable if so equipped. Remove the PCV valve hose, the air regulator hose, the BC/CD hose, and unbolt the EGR tube. Disconnect the fuel temperature sensor wire and unscrew the intake collector cover. Remove the water hoses from the bottom of the intake plenum. Remove the 5 intake bolts. Lift up on the intake collector. Remove the gasket. Always cover the intake runners to prevent contaminations from being introduced into the engine. Next, remove the bolts securing the fuel tubes, followed by the bolts securing the fuel injectors. Lift up the tube and injector assembly and place on a suitable work surface. To remove each individual injector from the fuel tubes, it will be necessary to cut the intermediate injector hose between the rail and the injector. Do not cut all the way through the hose with a knife, as damage to the tube may result. Once the outer jacket of the hose is split, it is a simple matter to pull the hose and injector off. When installing replacement injectors from Hygrade, the fuel hoses are supplied with the injectors. Always wet the inside of the new injector hose with fuel and reinstall the hose and injector onto the rail. Caution: use high-pressure fuel hose if replacing the hoses separately. Always use new hose clamps. With all the injectors replaced, reinstall the injectors and the fuel rail. Always utilize new O-rings. Don't forget to install the spacers. With the rail in place, reinstall the intermediate spacers and torque the bolts in place. Reinstall the collector using a new gasket. Don't forget to torque the collector bolts. Connect the fuel hoses using new clamps. Bolt up the EGR tube. Install the collector cover, the BC/CD hose, the air regulator hose, the fuel pressure manifold vacuum hose, the PCV valve hose, the air cleaner duct, throttle cable, throttle valve switch, and other componentry removed to aid in disassembly. Charge the fuel rail and check for leaks. Start the engine and road test. As you can see in Mode 5, no trouble codes are present. With the vehicle returned to the shop, recheck the engine idle speed and readjust as necessary. I would like to take this opportunity on behalf of Standard Motor Products, its Hygrade division, and its training department to thank you for purchasing this video. And we hope that you will consider us for your future replacement parts needs.